It is time for everybody's favorite chemistry part in the whole world, stoichiometry. For those of you having a mild panic attack, relax. We're actually not really going any further than we did first semester. We're just going to circle back and hit a little bit of gas stoichiometry. We normally go beyond a little bit and throw some Pivnert problems into it and that kind of stuff, but we're really just going to kind of do a little bit of gas stoichiometry. It's the last new thing in this unit. We'll hit some problems today. A few more practice problems of this and other kinds on Tuesday. Wednesday, just work all kinds of different problems, just hitting a few different types of things. So go back and look at some of the quizzes where you've missed some questions, especially the big quizzes where it wasn't just daily quizzes where you kind of given answers that we had helped you with and stuff. Figure out what type of problems you need to work and work a few of those types of problems anyway, right? But anyway, going on to gas stoichiometry. What we need to be able to, there we go. What we need to be able to do, as we always have, is change things into moles and then convert from moles of one type of thing to moles of another and then convert back out. So there are several ways to do that. First reminder here, right? Remember, 1 mole of gas, if you're at STP, takes up 22.4. That's a Pivnert problem. If you plug in 1 atmosphere of pressure, solve for volume, 1 mole, 0.08206 liters atmospheres per mole Kelvin for R, and 273 0 degrees Celsius, 273 Kelvin, the volume you get is 22.4, right? That's where this 22.4 comes from. That's an answer to a Pivnert problem. So that's why, but we have to be at that specific STP, right? So some ones, quick reminders. If you've got grams, you need to change to moles, or have moles, you need to change to grams. You use molar mass. Liters of solution. So we're not doing a whole lot of this right now, but the common problem that students will have is when they see liters, they're not sure which thing to deal with. Do I deal with molarity or do I deal with 22.4? And students will tend to want to throw 22.4 in when they can't. So if you've got a solution-y kind of thing, right, a liquidy kind of thing where it's dissolved in water, that's molarity, not morality, right? Molarity. They're going to have to give you that number on the problem, 2 molar, 3 molar. That's the titration-y stuff we did. If they give you atoms, you use 6.02 times 10 to the 23rd. Atoms or molecules or whatever, right? What we will be using mostly this time is kind of grams-y stuff and liters stuff, right? So liters of gas, if we're talking about gases, balloons, lungs, atmosphere stuff, right? That's going to be, if you're at STP, that's 22.4. If you're not at STP, it's a Pivnert problem. We might, I'm torn on this. I normally do a few of these, but only ask students to ever do it like once. This year, we're trying to back off a little bit. I probably won't ask you to do this on a test. Okay, we're not going to ask you to do a Pivnert problem from stoichiometry on a test. You'll get a Pivnert problem on the test, but it won't be like a stoichiometry problem that then rolls into a Pivnert problem. When you compound problems like that, that makes it harder on students. If you're getting gas stuff, problems that I'm asking you to solve, you're going to be able to use the 22.4 liters per mole. Or if it's talking about gases, it's talking about STP, you can use that 22.4 liters, goes with the liters part, 1 goes with moles. So chemistry is the thing we learn by doing, so let's work a problem. All right, so we've got a fictional chemistry teacher, Fred Exotic. He was told by his wife to shave his glorious mustache. This totally fictional character wanted to pay someone to snuff out his wife. Apparently, this fictional character was not happy about shaving his mustache, so he wants to snuff her out. Well, one way to snuff somebody out is to just cut off their supply of oxygen. And so what he wanted to do was generate enough carbon dioxide to fill a small room. So how much baking soda would you have to decompose? He and this whoever he was paying to snuff his wife out, right? So you're going to take baking soda and heat it to generate carbon dioxide. Now, if we think about this question, you're going to need a chemical reaction, right? So that's the first thing we need to do sometimes. You did this, right? You heated baking soda and decomposed it. So this is how you would do that, is you would heat the baking soda, decompose it, and generate carbon dioxide gas and stuff, right? So we're going to go ahead and jump to the board and do that through the magic of cinematography. We've got baking soda, sodium hydrogen carbonate, NaHCO3, turns into sodium carbonate, Na2CO3, water, and carbon dioxide. So if we're going to do stoichiometry, we better balance this thing. I've got 2 sodiums right here, so I'm going to put a 2 in front of my sodium here. That's going to give me 2 hydrogens. Well, I've got 2 hydrogens. That's going to give me 6 oxygens. Well, I've got 3 4, 5, 6 oxygen. So it's already balanced with a 2, 1, 1 there, right? I'm going to go ahead and hit the lights. Maybe that will help with the glare. Seems like we've got a little bit of glare there, right? So we've got 2,300 liters of CO2 that we want to generate, right, in this room. So 2,300 liters of CO2 gas. The conversion, if I want to change chemicals, right, I've got to cross the mole bridge. If I'm going to cross the mole bridge, I need to have everything in terms of moles. So if I've got 2,300 liters of carbon dioxide, we'd say, well, for every 22.4 liters of CO2, it is 1 mole of CO2. Right? Oh, and I think for Higgins students, I think she tends to put these in parentheses, right? Which is just fine. That just bundles them together so you can see them easier. Historically, I haven't, but it's the same. Either way works just fine, right? So anyway, we're going to rotate a little bit so we can see a little easier here. I've got it in terms of CO2 now. So now I need to cross the mole bridge. My mole bridge from CO2 to baking soda is a 1 to 2. I need to write all of my units so I can tell which one goes on top and bottom, because it's 1 mole of CO2 for every 2 moles of baking soda. Right? That gives us our baking soda. I'll go ahead and put parentheses around it again. Mathematically, they're not really necessary, but it is nice to kind of see them there that way. And then we're kind of looking at the same thing. And they said, how much baking soda? Well, baking soda, you don't do by the mole. You would measure the amount there by the grams. You would weigh it, right? When we say how much, it's a powder, right? You know what baking soda is. So you'd want to know what the weight of the thing is. So I need to do a side problem. So I'll step off to the side here and do a side problem. I've got sodium, which is 22.99. I've got hydrogen, which is 1.01. I've got carbon, which is 12.01, and oxygen, which is 16.00 times 3. Right? We've got all of those with each of those. I don't need to worry about the 2 here. That 2 got taken care of right here. So I don't want to worry about that when it comes to these things right here. Man, that glare, let me stand in front of the glare so you can kind of see those numbers. But hopefully you know how to do a molar mass. I know it's been a little while for some of us, but plus 16 times 3. So that gives us a molar mass of 84. So our molar mass then is 84.01 grams of baking soda for every 1 mole of baking soda. Right, so 2,300. Then we just multiply by the top, divide by the bottom. 2,300 times 2 times 84.01 divided by 22.4 is going to be, oh, that's a lot. They're going to need a lot of baking soda. 172,520. Let's see, it looks like we've got 2 sig figs, so 17,000, so 170,000 grams or 170 kilograms, which in case you're curious, 170 kilograms times 2.2 would give us 374 pounds. That's a lot. Right, so you need 170 kilograms or 374 pounds if you want something more realistic, right? But mathematically, this is what we get. This would be our sig fig answer, and we've got one that big. I kind of like to change it into kilograms. Okay, so we solved the first problem. Now we need to try another problem. Now, first problem, you probably just kind of watched me do. With this problem, it wouldn't be a bad idea to go ahead and try and do some parts of it on your own. As you try and do those parts and come into figure out where you're having some trouble, and then you run it, then hopefully I can help you through that, right? So we've got bored fictional biology teacher, Carol Honkins. She is tired of being cooped up in her house with nothing to do. She decides to light her farts on fire. Don't do that. It's not safe. You can catch yourself on fire, right? So what volume of carbon dioxide would she produce? Oh, I didn't give you any stuff in this problem. I didn't give you any, I didn't give you like a volume of methane. I need to give you a volume of methane for this problem. You can't do this problem without that. Let's say she has a 1 liter fart. We'll just make life easy and say she has a 1 liter fart. I can't type that in on here because it's a video. Okay, so she has a 1 liter fart and she wants to know, and she's going to catch it on fire. So this is a combustion-y kind of thing. So maybe try and write that equation on your own, right? Methane is what farts are made of. We know what the other reactants got to be in combustion. So then we can figure out what our products are and stuff. All right, so we're working the problem now. They gave us methane, CH4, and they didn't give us an equation, but they did tell us it burns, right? We know methane burns. You burn that in Bunsen burners and all that kind of stuff. Well, when we burn, when we have combustion, that is plus O2, and we should know all of our hydrocarbons are going to burn to make CO2 and H2O. Right? If it's complete combustion. If there's not enough oxygen around, then you make carbon monoxide instead of carbon dioxide, right? That's that incomplete combustion. That's why we have to change our furnace filters. That's why you don't run the car in the garage with the door closed, because you run out of oxygen and make carbon monoxide, which is not good, right? So we're going to take this 1 liter fart, 1 liter of methane, and we're going to burn it and see how much carbon dioxide we make, right? What volume of carbon dioxide we make. Is it a good assumption that we're at STP? Probably not, because inside the body, it's going to be under a little bit of pressure and it's going to be warm, right? So it's not at STP, but whatever. We're just doing that to make these problems manageable, right? I'm not going to ask you to do a bunch of problems not at STP. Might do one tomorrow where we roll a regular Pivner problem into it. But we've got our 1 liter of methane. My L's always look like 2s. That's not a 12, that's an L, right? My 1 liter of methane. It's a gas. We're claiming it's at STP. So we'd say, well, 22.4 liters of methane. I started to write CO2. 22.4 liters of methane for every 1 mole of methane. Then we need to do a mole bridge. Not balanced rounds. So let's go ahead and 2 there for my hydrogens. And that gives me 4 oxygen. So 2 there. It still ends up at a 1-to-1 mole ratio. So 1 mole of methane for every 1 mole of CO2. And now we've got moles of CO2, but we wanted volume of how much volume of CO2 we're going to generate. So we'd say, well, for every 1 mole of CO2, it's 22.4 liters of CO2. And there we go. You might notice something mathematically. There's a bunch of 1s here that cancel out, and 22.4s cancel out. Well, because they're both gases, and they're at the same temperature and pressure. They don't even have to be STP. They just need to be same temperature and pressure. This conversion would be the same because gases act the same. So really all that matters is the mole bridge. So since we happen to have a 1-to-1 mole bridge, 1 liter will give us 1 liter. Not all gaseous reactions are 1-to-1 mole bridges. So you can't say how many liters is always equal number of liters, but you can say that the mole bridge is the only thing that matters if they are at the same temperature and the same pressure. At least for your problem. Now in this, again, we're catching something on fire. That's not a good assumption, but we're going to use that assumption, right? So the 22.4s are going to cancel out. So it's a little factoid thing. We mentioned it first semester too, but I don't, it might not be something you remember. But the nice thing is you can always use those if you need to. You don't have to remember that you can leave those out. But since it starts at a gas and ends at a gas, and there's no temperature or pressure change, you can cancel those unit conversions out there, right? And just do a liter to liter conversion. All right, that's the second problem. Let's work one more, a little bit harder problem. Last problem, a little less silliness on this one. Component that makes something explosive is generating a lot of gas, right? Because then that builds up lots of pressure, and that causes a lot of damage because it causes things to pressure can cause forces and things like that. You might not even remember hearing about it. When I was a kid, one of the big things that happened, and I remember sitting around the TV and watching it, was the Oklahoma City bomber. I was a little kid. I don't know what he was upset about, but he was upset about something, and he tried to blow up a building there in Oklahoma City, which is really tragic. But the people rallied around it and fixed the building and caught the guy who did it and all that kind of stuff. Anyway, the Oklahoma City bomber used ammonium nitrate. A lot of people who hurt themselves trying to make bombs and stuff try and use ammonium nitrate because of the reaction that's below. It's a really good fertilizer, but you've got to be kind of careful with it because you can hurt yourself with it, right? So this is our reaction. The Oklahoma City bomber used 2,300 kilograms of ammonium nitrate. We want to know how many liters of gas he would get at STP. All right, let's work the third problem. This one's third time we've done this. So a good idea to pause and try and work ahead of me several times. Got the equation that they gave us in the problem. We have 2,300 kilograms of ammonium nitrate. They're asking us about total moles of gas that were formed. So I know I have to do a mole bridge, so I'm going to need to change to moles. They gave me a gram kind of thing, so I'm going to need a molar mass. right? Nitrogen is 14.01 times 2. So that's 28.02 because there are 2 nitrogens there. Hydrogen is 4.04 because there are 4 hydrogens. Then we've got our oxygens at 16.00 times 3. Right, so that's going to give us our total molar mass. I don't need to worry about this 2 because we're going to deal with that in our mole bridge. So I don't need to worry about that 2 right here. So this is going to be 80.06, right, grams per mole. Now notice that's grams per mole, not kilograms per mole. So I need to change my kilograms into grams. We know we can change kilograms into grams because we can just move the decimal place. How many places are we going to move the decimal place? 3, right? So 2,300 kilograms is 2,300,000 grams of ammonium nitrate. Right, we can see that okay. Let's rotate just a little bit. Sorry about the glare. I keep trying to shut the lights off, but I'm remaking a lot of videos because when I shut the lights off, the video gets really laggy and doesn't work very well. So I don't know if I don't know why that is, but I apologize for the glare on the board. Not much I can do about that. We've got the ammonium nitrate here, grams of ammonium nitrate. So I'll put 80.06 grams of ammonium nitrate on bottom for every 1 mole of ammonium nitrate on top. This one's a little tougher, this mole bridge step. The bottom part's pretty easy. I know it's going to be 2 moles of ammonia on bottom. But on top, we don't care what the gas is. We just care that it's a gas. So we would add all of these together and say 7 moles of gas is what we're dealing with there, right? Not 2 moles of this and 4 moles, but just 7 moles of gas. If we want to know about grams, we'd have to do 3 separate problems. Like, well, how many grams of products? Well, how many grams of products would be 2,300,000 grams because of the law of conservation of mass. But since they're all gases and we're just caring about the total thing of gases, we can just lump them all together because all gas particles act the same, right? Pressure-wise and volume-wise and that kind of stuff, right? So then we'd say, well, for every 1 mole of gas, it is 22.4 liters of gas. And then we just need to multiply by the top and divide by the bottom. Is it a good assumption that this gas is going to be at STP? No. When you have explosions, they're at elevated temperatures and elevated pressure. So you're by definition not at STP. But we're just I'm trying to give you some problems with, that are real world problems and I don't like saying interesting about something exploding, but I also don't like just lumping a chemical and saying a chemical is evil. Yes, this chemical can be used in explosions, but it's also a common fertilizer. And without common fertilizers, we can't feed 7.5 billion people on this planet. Right. So I don't like to just say a chemical is evil. Anyway, we've got 2.3 times 10 to the 6th grams times 7 times 22.4 divided by 80.06 divided by 2. That's going to give us 2.3 times 10 to the 6th liters of gas. Right. Just kind of worked out that time. So to 2 sig figs, 2.3 times 10 to the 6th liters of gas. Hopefully that helps. Keep working problems and all that kind of stuff.